Okay, welcome back to CS103. We're going to have a quick look at where we finished last time. Last time we mucked about with models of numbers made from physical objects that you can buy in a shop. And part of the point of that was that these things are data. They just sit there. They don't do anything, but we can see them. We can inspect them. We can tell the spuds apart from the lemons. And that's how we compute. So we invented a notion of number, which you can see here. Clemens is helpfully pointing. So when we say data, we're saying, I'm inventing a new type of thing that you've never heard of before. And I'm calling it number. And then there are two ways of making a number. There's capital Z, which makes a number on its own. And there's capital S, which makes a new number from an old number. And remember, I need to get used to learn to read properly. Things that begin with a capital letter are themselves. They don't stand for anything. They're like proper nouns. And you can tell from the fact that they have different names that they're different things. So capital Z, capital S, they don't mean something other than themselves. They just are things that sit there, like a lemon, that's the Z, like a spud attached to an existing number. They just sit there being data, being stuff you can do computation to, but they're not active themselves. Meanwhile, things that begin with a lowercase letter, like 4 here, stand for other things. They're like common nouns. This 4 is a new name for an old number. So this SSSSZ, that's an existing number built with the two ways we have of making numbers, the Z and 4 of the S's. That number already existed. It came into existence when we declared data number. But we're giving it a conveniently shorter name, 4. Okay, and then we defined addition. So this thing, you can see it's made of symbols rather than letters. And that means it's an infix operator. When we feed it 2 inputs, we write it between those inputs, like you're used to. When we talk about it as a thing in its own right, we put parentheses around it. So if we want to talk about plus the function, we put it in brackets. If we want to add 2 numbers, we just put a plus sign between the numbers. So that's a key thing. And what we're saying here is that plus is a function which takes in 2 numbers and gives out a number in return. So that's to say, I mean, you can add 2 numbers and you get a number, right? We're not saying, we have a notation for saying a familiar thing. It's an unfamiliar notation. I'm trying to make sure that there's as few unfamiliar things that aren't the unfamiliar thing I'm trying to focus on. So we're talking about adding up as a thing you know how to do. What's a function, by the way? A function is something which has a clearly defined collection of valid inputs and delivers for every valid input an output in a predictable way. That's to say, if you put the same input in to the function another time, you will get the same output. The function doesn't look to see if it's Friday and decide to do something different. The rest of us might do that, but the function has to behave the same way on the same input no matter what you do. And to be a function, it has to deliver an output for every input. If it just, you give it an input and it buggers off, then it's not a function. Now, you'll find that in other programming languages, things are called functions which are not. Things are called functions which go horribly wrong. if you decide, you could implement addition in other programming languages, such that if you choose to add 2 and 2, it deletes your hard drive. In ask, a promise is a promise. You put in 2 numbers, you get a number. And to keep that promise, you have to explain how come your program covers all the possibilities. So when you declare data number, you say there are 2 possible ways of making numbers, with 0 and with successor. And to explain how to compute with the numbers, you have to make sure that's covered. So what happens is, you explain what the possibilities are. Ask says, cover these possibilities. Exactly reading your definition to tell you what you have to do. Likewise, we also said there's a terribly important thing about numbers, which is that you eventually get to the lemon. If you work your way along the potatoes, you can't keep just walking along the potatoes forever. The number will get smaller and smaller and smaller, and it can't get smaller forever. You eventually get to the end of it. And that's why computation with numbers actually works. So when we write addition here, we start by saying what promise we're relying on. So inductively n means, it's part of the explanation of why the program works. It doesn't contribute to what the program does, but we're about explaining as well as doing. So what we're saying here is this process, n plus m, is relying on the fact that when we take n apart, we'll eventually reach 0. So we're explaining why on earth this recursive definition works. You can see this is a recursive definition. If you look at the second equation, there's a plus on the left, there's a plus on the right. We're defining plus in terms of itself. So that's a scary thing, to define something in terms of itself. And it requires an explanation. I don't know, folks, if you were awake politically when Theresa May said Brexit means Brexit. But as a computer scientist, I can tell you that that's a completely meaningless thing to say. That's an example of recursion, which is just nonsense and has no explanation for how it gives you any traction on anything. So that's an example of bad recursion. In CS103, recursion will always come with an explanation. And what we're saying here is that addition works because we keep making the first input smaller, and we can't make it smaller forever. So what we say is, if you're adding 0 to a number, you're done. The output's the number. If you're adding successor of something to a number, add the something, and then put the successor back. Put the potato back on, take the first potato off, finish the addition, put the potato back. All right? And then we actually ran the program. We tested 4 plus 4, and because 4 is successor of successor of successor of successor of 0, then the equations tell us how to add 4 to 4. And we end up with 8. Isn't that reassuring? Okay, look, no hands. Clemens is doing the work. Let's recap these proofs. So you can see, right, so the important thing to understand with ask is that it hasn't been to school. It doesn't know stuff that you know. It only knows the stuff you've told it just now. So ask knows nothing about how plus works other than the definition we've just given. It's completely new. However, you can see that the first thing we're trying to prove, that if you add 0 to something, you get the something, that's actually part of the definition of adding. So this should be true if you just test it. So test is a proof strategy, which means use the definitions to compute and see what that gives you. And here, we find that testing is enough to show the first equation. But testing is not enough to show that if you add something to 0, you get the something. Because all ask knows is the definitions. And what you see is that the definition relies on knowing whether the first input is 0 or a successor. And here, in this equation, on the left-hand side, the first input is x. And it's not clear whether x is 0 or a successor. It could be anything. So when you see a lowercase variable in a thing you're asked to prove, you should consider that basically that variable belongs to the devil. You're trying to prove something, and the devil can make it whatever she wants to mess with you. So you have to be ready for anything. You have to show that no matter what the devil chooses, she's not going to have any luck. All right. So we're going to have to... So the key question when you're doing these proofs is... the way you do these proofs is to provoke some computation. And the way you provoke computation is to go back to the definitions and look at what they need to know. This definition of plus needs to know what the first input is. So we're not going to make any progress on the proof unless we force it to tell us what the first input is. Also, we need to explain how this process works. So the explanation of why the proof is good is going to be very closely related to the explanation of why the program is good. So the program plus works by making the first input smaller. And this proof is going to make sense only if we promise to make the first input smaller. So we're going to do, the explanation is going to be as inductive as the program was in the first place. And if you're trying to get the message, here's a message that is not a very secret message concealed within CS103, is that the business of programming and the business of proving are really very, very similar indeed. So when I hear people say, I like mathematics, I don't like programming, I hear, I like mathematics, I don't like mathematics. Right. You know, bad news, folks. Programming done properly is mathematics. You know, programming only stops being mathematics if you're allowed to do it wrong. And unfortunately, the world has sufficiently few competent programmers that it's forced to pay incompetent programmers, and that's why everything's rubbish. You know, so I'm, you know, trying to get you on the good team. Right, let's knock this off.
Let's send it. Wait a second.
And yes, it's running like treacle. So yes, nothing has changed to the goal, except that we've installed the fact that the explanation means x is going to get smaller. And we are entitled to assume that for every number smaller than x, our result is already true. And that's okay, because, you know, so we're relying on the fact that it was true already for the smaller numbers, and numbers can't get smaller forever. So that's why this explanation makes sense. All right. So the next thing we need to do is to provoke some computation. And in ask, the strategy we use for that is from. So when you say from, and you say a particular variable, here we're going to choose x, you're asking, where did you come from? How were you made? What's the reason behind you? What are the possibilities? So here there are two. So once again, ask is saying, is looking at the definition of number. So the fact that we're working with things of type number tells us a proof method. It tells us that we need to consider two cases. What happens if x is 0, and what happens if x is successor of something? Now, so ask thinks there's two possibilities here. We could be checking if 0 plus 0 is 0. Oh, that's just true by arithmetic. So it figures out that that possibility is so simple. It can just calculate it, and it doesn't even bother you with it. That's why we only get asked what to do with the successor case. And then, here we're saying, well, okay, what happens if the number is bigger than 0? And you can see that we've now got a problem where one of our equations, our defining equations, could do some work. So we might make some progress if we actually ask for some computation, and you do that again with test. So
let's have a look whether this works.
yeah.
Send.
And you can see that we're done. The prove changes to proven. When we first built this system, what happened when you won was that your program came back exactly the same as when you sent it, and nobody got any dopamine from that. That was, that was rubbish. So we changed it so you just get a little acknowledgement that you've nailed it, and it became a much better game. Okay, so, but it's all magical. One of the things you'll find about ask is that when you're winning, you will be done one step sooner than you think, because ask is too bloody clever. So what's happened here slowly is that it has it's done the computation. So it's turned successor of x prime plus z into successor of x prime plus z. That was what the equation said to do, right? The next thing that happens is that it sees that it's got successor on the left-hand side and successor on the right-hand side. And when you have an equation between two things that begin with constructors, so 0 and successor are called constructors, they just make stuff. The only way two successors can be equal is if the things they're successors of are equal. So ask gives you that for free. It cancels the successors. And what's left is the equation x prime plus z equals x prime, once you've cancelled the successors. And that's a fact about x prime, which is known to be smaller than x. And because we're working inductively, that means we know that already. And because we know it already, ask doesn't bother you with it. So it's quite a lot of things the machine is doing for you that you need to get a little bit of a model of. So thanks, Clemens. That's that. I can tell this lecture is going to finish long before the material I planned is going to happen, but let's go. But I don't mind going slowly. I want to go slowly and make sure you're with me. In fact, so if I'm leaving you behind, slow me down is my message. Let's do the next one. So here we're actually going to prove that it doesn't matter how you bracket the adding up, that you end up with the same answer. This is called associativity. That's the fancy word of the day, is plus is associative. Just that means you can group things however you want. Yep. All right. So I want to teach you the art of playing a game called Why Is It Stuck? That's the key. If you can learn to play Why Is It Stuck, you will nail this module. All right. So the point is that from the very definition of plus, you can see from the from it does that plus is desperate to know the truth about its first input. So plus is stuck if its first input is stuck. Variables are stuck. So we look at the left-hand side of this equation and we see x plus y plus z. And that's stuck because x plus y is stuck. And x plus y is stuck because x is stuck. Are you with me? Look at the right-hand side. It's x plus y plus z. That is stuck because x is stuck. So both sides of the equation are stuck because x is stuck. That's 2 votes for x, no votes for anything else. We know where to hit this. You know the old story about the woman who calls out someone to fix her washing machine, and the engineer thumps it and charges her 100 quid. And the owner of the washing machine said, "That's a bit steep, isn't it? 100 quid for just thumping it." And it's like, it's 20 quid for the call out and 80 quid for knowing where to thump it. So I'm trying to teach you where to thump it. We figured out we need to thump x. So we start with inductively x, and then we do from x to make some computation happen. And the tension is palpable. Once again, we don't see a case for 0 because that's arithmetic is enough to get rid of it. Ask doesn't bother with us with it. But we do get a case for successor. You can see that, can you put the brackets in, please, Clemens? So plus associates to the left. So, yeah. So that's the way to read that left-hand side. So ask doesn't print unnecessary brackets, but sometimes extra brackets are helpful, and you should feel free to add them in the right place. Okay. So the next step is to get the computation that we wanted, and that is done with test.
Let's see.
And once again, we are home just by arithmetic. What happens? We use the equations. The successors bubble to the front. They cancel, and we're left with a goal, which is talking about the same thing one step smaller. So the inductively gives us the thing we need. So what happens? The successors disappear, and we end up with the same thing about x prime that we wanted for x, but x prime is smaller than x, so we already know it. Okay. So that's the basic proof technique that we start with, is looking at the definition to see what the explanation is and mimicking the explanation in the proof. The proof goes the same way the program goes. And you pay attention to what information the program needs to do a bit of computation, and you make sure in your proof that you feed it that information, and then because the program simplifies, the proof simplifies. So that's so the message is 3 strategies that go inductively, and then you do enough from to make some computation happen, and then you test, and here you get lucky. This is deliberately engineered to be easy. Sometimes there's more to it than inductively from test, but everything at least starts with inductively from test. So your homework, which is already online for next Thursday, is a bunch of programming and proof examples that are very much like this. And I promise you that I have constructed them very, very carefully so that you can kick them to death with only inductively from and test. So if you can learn the lesson of this lecture, you can do your homework for Thursday. There will be other proof methods we'll need when things get trickier, but I want to get you the hang of the basics, right? Okay. So let's at least, we got, you know, maybe 10 minutes left. Let's see if we can scale the giddy heights of at least defining multiplication, if not proving things about it. And you can see further up, we said that plus associated to the left and had priority 5. And here we're saying that multiplication, so this infix L, the L means left. This is, I didn't choose it. So ask is based on a programming language called Haskell, which we will teach you next year. And I'm trying to kind of warm you up for it. So this says that plus has priority 5 and it groups to the left. And we're now saying that multiplication has priority 6 and it groups to the left as well. So when at school you had something called BODMAS drilled into you, I suppose. No? Well, ask doesn't know anything about that, so we have to tell it. So what we're saying is, what you're used to is what's going to happen. But we have to say something to make that happen. All right. We got lots of choices. I mean, we know how to add, so we ought to be able to figure out how to multiply, because multiplying is just adding up a lot. We're close to the end of the lecture, so I'm going to make the arbitrary decision that we're going to go inductively on B. So we're going to add up a bunch of copies of A. How many? B many. If we add up B many copies of A, we'll be good. So we go inductively B. And
we do from B.
From B.
And now we have 2 cases.
Yeah. So, yeah, we do. A times 0, right? No A's. How do you add up no things? What's the total of nothing? Nothing. Nothing will come of nothing. So A times 0 is 0. And then if we want to add up successor of X copies of A, we better add an A. And then some more.
We add an A and then some more, right?
Yeah. So we still need another X of those. We've got the first A corresponding to the spud. Oh, that's my you notice, by the way, okay, I should say this. You notice that the previous lecturer kicked out on time, except that yous were all in the way. So let me point out that door. You there. The previous lecture will kick out that way. You come in this way. Everything will be fantastic. All right. And the same goes in about 5 minutes' time. Right. So we've got addition. It's is it defined yet?
It's about to be defined.
Yes. It's defined. Okay. I think we should do a test. So you can use the test command. Let's test 4 times 4, shall we?
Yeah, that's useful.
And then
okay, 1 second.
Yes,
here we go.
And then if you count very carefully, you'll see that there's quite a lot of successors.
It's 16.
So you should understand that I'm a professional mathematician, and correspondingly, I'm not allowed to commit acts of arithmetic in public. In fact, I'm also a professional computer scientist, and the art of being a computer scientist is to go, counting goes 0, 1, that's too big. So, I mean, yes. Once numbers get bigger than 2, we make machines do it.
I also added 2 times 4 just to be safe.
Cool. Yes. All right. So where are we going? Let's at least look at the cliffhanger. This is what's always going to happen: is that there'll be a lecture plan. I don't get to the end of it. Is we might even think about this. So we might have a couple of minutes, right? When we defined adding, we noticed that there was a very particular number that did nothing when you added. Can you think of a number which does nothing when you multiply? Fantastic. So we call this the neutral element of whatever the operation is. And it's very often the case that operations we care about that take 2 inputs have a neutral input, of a neutral element, where if you feed that in one input, what you get out's the other one. The do nothing. It's always important as a computer scientist to ask yourself, what's the right way to do nothing? So we figured out that we want to prove that A times 1 is A and 1 times B is B. I don't know. Let's go out on a high. Why don't you hit?
This one is just test, right?
I think it's the other one that's test.
Damn it. You're
test.
right. I want to finish on a low. So.
Right, because multiplication wants to know about its second input, and here we're saying the second input is actually known. It's 1. Right. So you hit send. And it's proven tested. Okay. How does that work? I want to do one last thing. Can you nip up a few boxes and comment out the proof that x plus 0 is x?
The proof that x plus 0 is x. Okay, where is it?
Yeah. So back in the top box, yeah? Just use braces or, oh, okay, fine, yeah. Comment that out.
Yeah.
And then hit send again. And we'll see what happens. Multiplication box. You see, it's now asking us, saying, this will work if A plus 0 is A.
Yeah.
And because we commented out the proof we did earlier, ask doesn't know that anymore. We deleted part of its brain. So that's the thing. The message here is that this stuff all builds, and ask will cheerfully make use of things you've taught it. So the fact that a multiplication does something sensible in this respect boils down to the fact that addition works. Anyway, I should stop, and I should absolutely kick out on time. Can we? I will leave the box in over here. I think that's the so the box is on this table. Right. Have a fantastic weekend.
Yes. You too.